Section 4.1, we're going to talk about some polynomial functions. So we're getting started in chapter 4, which is all about looking at polynomials. So we're really focusing our attention on things like x to the second, x to the third, x to the fourth. So our polynomial parent graph. So only whole number exponents. This entire chapter, we're going to be looking at how to find their solutions, what their graph looks like, all of that. So in chapter 4.1, we're going to just explore what are polynomial functions just in general. So first thing is just some terminology stuff that we need to be clear on. So we're going to talk about these first few ideas. So the degree of a polynomial, we'll start with that. The degree, if you remember, is the highest degree term that you have in your polynomial. So the degree of a polynomial, the highest degree. Coefficients are the number parts of the term. So when you look at the number part, it's what tells you how many. So if you have, for example, 3x squared, something like that. So if we look, whoa, my goodness, my whole screen is moving there. Somebody slammed the door. 3x squared, the 3 would be the coefficient, the 2 would be the degree. So we're looking at those values. Leading coefficient then, this is really important. It's the highest degree term's coefficient, so the number part of that highest degree term. So when you look at your polynomial, it would be the highest degree term, the number part of that. Why do we care about these at all? Well, the degree tells us something about end behavior. If I tell you it's degree 4, you know what the ends of that graph look like. The leading coefficient tells you things like, if it's the 3x squared, for example, the 3 tells you that it's vertically stretched. If it were negative, it would tell you that it's reflected. So those two pieces of information are really critical. All right, so what we're going to be looking at then specifically for these polynomials, just understanding that terminology, is what the zeros of these functions are, these polynomials. So a zero of a function means the values for x that make the function 0. So what numbers can we put in for x that will give you a 0 for your answer for the polynomial? So if you think about what that means, when p of x is 0, that would be the places where y is 0. So think about where y would be 0. If you have ordered pairs where the y value is 0, all those points are on the x-axis. So another thing that people will think about is they'll say x-intercepts. That's where your real solutions are. So they'll be the places where it crosses the x-axis. But these zeros, other words that people use for them, roots, solutions, they're not necessarily always real, right? Because you don't have to have graphs that necessarily cross the x-axis. So especially with those even powers. So we're going to be looking at how do we find those imaginary solutions as well. But we know we can find those places in a lot of different ways, and that's what we're going to be looking at in chapter 4. So how do we find those places where x makes the function 0? All right, so let's practice really quick those first few terminology things, and we'll get into some pictures. So state the degree and the leading coefficient. So take a look at the function. Make sure you look all the way through. It may not be in descending order, and this is the term that we're looking for. So the degree of that polynomial would be 4, and the leading coefficient, I'm just going to abbreviate here, would be the number part of the term, would be a 9. So I know what the end behavior looks like. Degree 4, it's going to be doing something like this at the ends, and the leading coefficient being a 9 means it's stretched. So just understanding those terms. All right, determine whether 2 is a root of that equation means, does 2, when you put that value of x in, make the value of the function equal to 0? So how do you suppose you check that? Plug in 2, see if it's true. So if you plug in a 2, we want to see if that, in fact, gives you a value of 0. Well, when you plug it in and do your arithmetic, and you will be able to use a calculator, scientific if you need to, check and see. Well, sure enough, that gives you a 0 for your answer. What does that tell me? Well, sure, it's a root. That means the point 2, 0 is a point on the graph. It's a solution to that equation where it's crossing the x-axis. It's an intercept. So meaning a root just means when you plug that value of x in, it makes the function 0. So determine whether 3 is a 0 of this. Now it looks like the same kind of question, they're just written a little bit differently. Technically, we ask for roots of equations, so notice it's just written as a regular equation, and zeros of functions. This is written in function notation. Ultimately, the question is asking you to do the same thing. They're asking you, does f of 3 equals 0 if you plug in the 3? Well, so we're doing the same thing. So we plug in the 3 and do the arithmetic and see if you get 0. If you do, it means it's a root or a 0. If you don't, it's not. And for this one, looks like, oh, that's 3 to the 4th. So that would be 81, 27, 48, and 9. Is that 0? And I don't think it is. When you do the arithmetic, I think f of negative 3, I think you get, oh, positive 3, sorry. I'm messing up what I'm running. I think the answer is negative 3. Double check when you plug it in. So negative 3 is not equal to 0. So what does that tell me? Well, no, it's not a root. It's still a point on your graph. It's an ordered pair. If you plug in 3, we got negative 3. That's a point on the graph. But it's not the 0 or the solution. So when we look at the values, it's not going to be that special place. So to find a 0, plug it in. Okay, so let's talk about how we find these solutions and how many solutions you have. We get to this very impressive thing called the fundamental theorem of algebra, which basically is talking about how many answers should we have in an equation that's a polynomial. So it says every polynomial equation with degree greater than 0, so that means like degree 1, degree 2, degree 3, has at least one root, or solution, 0, however you want to say that, in the set of complex numbers. That's what we talked about in that little review section right before. So things in the form a plus bi. So it could be just real, could be imaginary. So it means there's going to be answers, and they're going to be of that complex number form. So that means real or imaginary, or maybe some of both. So what we're going to do right now is just explore some pictures to get you thinking about what kinds of graphs could generate these types of solutions, these polynomials. So we'll start with degree 1, which is linear. We're going to try to draw some pictures here. If you have a linear equation, a slanted line, how many times will it cross the x-axis? Well, if you have a slanted line, it's going to have to cross at least once. So we have one real solution. I would call it distinct. It's its own number. And that means we have one x-intercept point. So if it's degree 1, we should have one solution because we have an x to the first power. So degree 1 has one answer. A slanted line is going to have to cross the x-axis. It's an odd power, so we know it has a real answer. But there's only one of them because it's degree 1. All right, let's talk about parabolas for a second. There's actually 3 different pictures I want to talk about for a parabola. What can happen for a parabola when you graph it in terms of crossing the x-axis? So I want you to think about that for a second and see if you can draw 3 different pictures. So go ahead and pause the video here and see if you can draw 3 different pictures of how a parabola could either cross or not cross the x-axis. All right, so here are the choices. We could have a parabola that crosses twice. We could have a parabola that only touches once. And we could have a parabola that doesn't cross at all. Now for all of these, I could have had parabolas opening down with the vertex below or above, depending on what I need to do. So they don't all have to open up. I'm just kind of showing that as my possibility. All right, so for the first one, there's 2 x-intercepts. That means there's 2 real answers, and they are distinct. We call that distinct, meaning different. So when you see the word distinct, they mean they're in separate locations. They're 2 different numbers, so think 2 different answers. And there's 2 x-intercepts. So we have 2 x-intercept points. It's crossing in 2 locations. All right, we'll look at the next one. There's only 1 x-intercept. But technically, this still counts as 2 real solutions, but instead of being distinct, this is called a double root. And this is a really important idea that's going to happen on a lot of graphs. This vertex point is an absolute minimum on your graph. Whenever you have mins or maxes on your graph, those are always going to be double roots. So double roots always result from maximum or minimum points. It's places where they're changing direction. So I'm going to make up an equation for this one. Say it was x plus 1 squared, whatever that might be. So I'm just saying I went back 1. So if you think about what that means, x plus 1 squared, the shift 1 to the left, that's the same as x plus 1 times x plus 1. It's happening twice. That solution is occurring 2 times. So that answer of negative 1 is happening twice. That's why they call it a double root. So technically it's 2 real answers. They just happen to be the same number. All right, what's the third possibility? Well, it doesn't cross at all. I still have to have 2 solutions though because it's degree 2. What kind of solutions do they have to be then? Well, they'd be 2 imaginary. So when you think back to doing quadratic formula, getting those imaginary solutions, that's where that's coming from. There's no x-intercept points. It doesn't cross at all. That means 2 imaginary solutions. So when we look at these imaginary answers, they always come in pairs like that. So there'll be 2 of them or 4 or 6, whatever it might be. All right, so the bigger the degree, the crazier the pictures get. So let's take a look at degree 3. I want to think about some of the different possibilities. We have lots of different graphs that we can draw. So I'm just going to talk you through a few things that can happen for degree 3. So think about this first. Does a degree 3 have to cross the x-axis? So think about pictures, think about the end behavior. Degree 3. Definitely does. And it can actually cross up to 3 times, because remember, if this is degree 3, I need to have 3 solutions. So I'm going to go ahead and draw one that has 3 distinct solutions so we can get a picture of what that would look like. So this is 3 real solutions, and they're all distinct. They're all in different locations. I have 3 x-intercept points. So maybe it crosses at -5, 0, and +4. That would be 3 different locations, 3 distinct real answers. All right, now is there a way to take that graph and only have 2 x-intercept points? So let's see if we can think about what that could do. So can I slide that graph up or down? And the answer is you can do either. So I'm going to slide it up. That's supposed to be just touching. So if you take this relative minimum from over here and you move that graph up so the relative minimum is on the x-axis, then you actually have 2 x-intercept points. How many solutions would it be though? Well, this is one distinct over here. This one, because it's a minimum, means it's a double root. So this one's a double. This one's distinct. So this actually counts as 3 real solutions still. So that's a 3 real answer, but because we have a double root. Well, I could have done that going the other direction. I could have dropped this original graph down and had this relative max be the point that just touches. So let's take a look at what that one would look like. So we have the relative max, and then we have our distinct solution over there. That would still be 3 real with 2 x-intercepts, because this one's a double and that one is distinct. So we have that option as well. So we have lots of different ways that that can look. All right, well, let's keep going with this. If I keep moving the graph up, what if I move it all the way up so neither the relative max or min is crossing over and I get something like this? Well, then it's only crossing one time. I have 1 x-intercept. How many solutions does it have to be? Well, I still need to have 3 solutions, but I only have 1 that's real. So I have 1 real, but I need a total of 3. So what do the other 2 have to be? Got to be imaginary. So I would have 2 imaginary solutions. So I have 1 real, 2 imaginary. And those are a situation where I could have dropped it down 2 instead. I could have dropped this graph that I had before down, and you could have had the other branch crossing. So there's lots of different ways to see this when you look at the pictures. But I could have done something like this, and it would be exactly the same thing. I would have 1 real, 2 imaginary, with only 1 x-intercept. All right, there's one more graph I want to talk about for degree 3 before we move on to degree 4. What about the parent graph, just y equals x to the 3rd? Just this guy. No turns at all. So always increasing. Y equals x cubed. The crazy thing about this, you have 1 x-intercept again, so it's the same as those last couple graphs. But the issue with this one is x cubed means x times x times x. So this critical point, that point of inflection, so we talked about max and min points, the point of inflection, also a critical point, that point of symmetry, something important is happening there. It's actually called a triple root because that value of x equals 0 is happening 3 times. So it's considered to be a triple root. So technically, it's 3 real answers. They just all happen to be the same number. And then when we're looking for that, then is they're all the same. So that would be 3 triple. So that's the name that you would get for that. Okay, so degree 4. Let's talk about degree 4 for a second. There's so many different graphs that can happen for degree 4. So I want to talk through some of these. For degree 4, think of the W shape. So the shape of the letter W, that's a really good way to start. So a W can cross 4 times. So if it's symmetric, I'm going to do one that's symmetric first. It can cross 4 times. So that would be 4 real. And they are distinct because those are all 4 in different places. So 4 real distinct solutions. You have 4 x-intercepts. Well, if you take this W, we can do it different ways. Now, if we take this W, is it possible to make it so there's only 3 x-intercepts? Well, if you drop that graph down, so this relative maximum in the middle is right at the x-axis, then we can get a situation where, oh, that was supposed to be touching. We're going to pretend that it touched. That would be 3 x-intercepts. but 4 real solutions because we have a double in the middle. So it's a double and then a distinct on each end. Abbreviate over there. So the double root, that maximum relative max, counts as 2 answers, so we actually end up with 4 real solutions. So we can have 4 real distinct, or we can have some with doubles. Let's see if there's another way we can make doubles. What if instead of dropping it down, I would have moved it up? So these absolute minimums, those points on the bottom, would have been on the x-axis. What about that? All right, so we have only 2 x-intercepts now instead of 3, so 2 x-intercepts. But we have 4 real solutions because each of these count as a double root. So still 4 real, but we have 2 doubles instead. So lots of different ways we can end up with 4 real solutions. All right, so let's move into the what if there's not 4 real solutions? Or no, let's do one more 4 real. What if it's not symmetric? So let's talk about a graph that wouldn't be symmetric. I'm going to make another one that would be 4 real solutions. What about something like this? So I have 3 x-intercepts again. 1, 2, 3. So 3 x-intercepts. But it's still 4 real solutions because I have a double over here and I have 2 distincts over there. So I have a distinct in each of those locations. So I have still 4 real solutions. So as you can see, there's tons of different ways to do it with 4 real. Okay, let's try to make some pictures of having some imaginary solutions. Is it possible that all of your answers aren't going to be real? So let's see if we can make a graph that would be 2 real and 2 imaginary. So I'm going to take this picture that I just did that had 4 real, and I'm going to slide it up so that double root isn't touching anymore. So how about something like this? So it's crossing in 2 places. So we have 2 x-intercepts, and that's it. So that means there would be 2 real solutions and 2 imaginary. And those 2 real would be distinct. They are in different locations. So 2 distinct, 2 imaginary. So you can definitely do that. You can definitely have that. What if you keep moving that graph up? I could just have something like this. That would still be a relative or an absolute minimum on there. Still be 2 real solutions, but I only have 1 x-intercept. But that would be 2 real solutions and 2 imaginary. The 2 real come from the double root. All right, so question for you. Is it possible to have a degree 4 that don't have any real solutions at all? Well, think about taking any of those w's and moving it up. No x-intercepts at all, so no x-intercepts. That would be 4 imaginary solutions then. So we have kind of the extremes. You can have 4 real, you can have 4 imaginary, or you can have 2 of each. So there's really a lot going on there when we talk about the different types of graphs that you can have. All right, so that's just to give you a flavor, an idea of what's happening with the pictures that you can draw. All right, so for the rest of 4.1, what we're going to talk about is how do you find these solutions then? What kinds of polynomials generate them? And then what kinds of solutions do you get? And we're going to go both directions. So we're going to use what's called a corollary, something that's related to the fundamental theorem of algebra. And I want you to circle, highlight, or star right in here. We have this polynomial. It looks really scary, but basically it boils down to this. Every polynomial that you are going to find out there, so every single polynomial can be written as a product of linear factors. Okay, what does that mean? Product means multiply. Factors mean things that are multiplied together to give you a product, an answer. Linear means degree 1. So every single polynomial can be written as x minus the root, all these little binomials multiplied together. But here's the key thing. The degree of the polynomial that you get is always equal to the number of the complex solutions that you have. That's what we were just talking about when we went through the different pictures. However many your degree was, that's how many complex solutions you'd have. That's how many answers you have. That's also equal then to the number of linear factors that you have to write as a product to make that polynomial. So we write everything as x minus a root, we can multiply those together and get our polynomial. So I want to finish this part 1 with being able to write those polynomials. How do we come up with the answers? All right, so take a look at this example then. We have 3 different roots roots that they're giving us. They say write a polynomial equation of least, super important, least degree. What that means is these are the only solutions you can have. Nothing's repeating, there's no doubling, nothing like that. It's just those three roots. Write that polynomial, what would it look like? And then we'll talk about what that means. So to write the polynomial, I'm going to use P for polynomial. It's x minus each of the roots that we have. So when you write it as a product of linear factors, those are the factors they're looking for. So these binomials, and we just put in the roots. So x minus a negative 3i, x minus a positive 3i, and then x minus 4. So we do that product. That will give you the polynomial. Now, no one would ever write minus a negative, so I'm going to go ahead and change that to plus positive. If you think back, that's just exactly like when we do our shifts, and we talk about, okay, what happens if we shift it to the left? That's where the plus is coming from. If you go to the left, that means it's negative. All right, let's be savvy here when we do our multiplying. I'm going to multiply the first two together because they're the complex solutions and they're opposites, they're conjugates. So that's going to make it a lot easier to multiply together. I would get x squared. The insides and outsides would cancel, and then we get minus 9i squared. Be really careful when you multiply those last together. Now, what is I squared the same as? It's a negative 1. So a negative 9 times a negative 1 is going to end up being x squared plus 9. All right, and we're going to multiply that by x minus 4. So this is just FOIL. We're just multiplying together. So our polynomial, FOIL that together, would be x to the third minus 4x squared plus 9x minus 4. All right, so I want to talk a little bit about this then, what this guy's looking like. It asks you, is it even or odd degree? Well, it's going to be odd because I had three different factors, so that means it's going to be a degree 3. And it's asking how many times should it cross the x-axis? Now, if you look back into what your zeros were, how many of those are real? Well, only one. So it should have one x-intercept point. It should only be crossing at 4. So I put it into my graphing calculator so you can see that graph. And sure enough, it's only crossing at positive 4. So when I think about the polynomial I make, that should make sense. Now, here's a question for you. If you take this polynomial, so this is the polynomial that generates those three roots. So if I multiply them together, I got this. What if I took this polynomial and say I doubled everything? I multiplied everything by 2. Would the polynomial that you get, oh, I'm sorry, this should be 36. I goofed. Make sure you have that on there. 9 times the negative 4, that should be a 36. If I doubled everything and got that, would that polynomial have the same solutions or roots as the one I just wrote above that I boxed? And it absolutely would, because I could just pull that factor of 2 back out and break it down into those products. So any multiple of a polynomial has exactly the same roots because you can always just pull out that factor. And if you go back to the corollary here, that's what that k constant is all about. If you multiply by a constant, it doesn't change your roots. Okay, let's talk about our last example for this part 1 here. It says write a 4th degree, with these three roots. It sure looks a lot like the same kind of situation as the last one, but it's 4th degree. That means it's going to be an even power. I need to have 4 solutions. Well, look at the roots that I give you. I only gave you 3. So the only way, if you look back at your pictures, to get a 4th degree with 3 solutions, you have one of them that's real. What has to be going on? So I'm only going to have one x-intercept. If you look back at your pictures, a 1 x-intercept with a degree 4, I know we have a ton of them here, 1 x-intercept with a degree 4 is going to have to be this situation right here. We have a double root happening. That's the only way that this can happen, because if you know you have 2 imaginary, this has to be a double. So which one is going to be doubling? Well, it's got to be the real one. You can't double an imaginary. Then you'd have 3 imaginary solutions. They always come in pairs. So if you doubled one of them, you'd have to double the other one. So it has to be just that one that's doubled. So when we write our polynomial, we're going to write 4 binomials, x minus the root, x minus the root, x minus the root for each of them. And remember, when you double that, each of these polynomials, that x minus 1, that's our double root, they have to be identical. All right, so go ahead, pause, do the multiplication, and check your answer. All right, so here's the polynomial you should have come up with. It's a degree 4. It's a double root situation, so 2 real, 2 imaginary. And remember, any multiple of this would give you the exact same answer. So the exact same root, so you could factor that out. So just double check your arithmetic. For our part 2 tomorrow, we're going to be looking at, okay, what if I give you the equation, the polynomial, can you find the roots? We'll go the other direction.